Okay, it's already started. Please go ahead and start the presentation.
Yeah, okay. So the topic of today's talk is about the locating source of the oscillation with two-tier dynamic mode decomposition to integrate the early stage energy of the oscillation. So I think we can start by sharing our perspective about the overall oscillation framework. And we think that this overall framework can be divided into two, which are pre-mortem and post-mortem oscillation frameworks. So in the pre-mortem framework, our prior objective is to find out how to prevent the oscillation which can arise in the power system with various frequencies. And as representative example, DMD and impedance-based oscillation analysis like these right figures. And based on this analysis results, we can take several actions like adjusting the gain of the controllers in many power system components so that we can prevent this potential oscillations. But in this post-mortem oscillation framework, because the oscillation has already happened in the power system, so our prior objective is to find out the accurate oscillation source as soon as possible. And our work also lies in this post-mortem oscillation framework. So its objective is to find out some generalizable oscillation source location method using the dynamic mode decomposition for both the forced and natural oscillation cases, and also for the low frequency and subsynchronous oscillation cases. So if you want some more information about today's talk, you can refer to our latest paper in here. And so in order to understand the dynamic mode decomposition, we should start from the SVD, which is the single value decomposition. And this SVD is an eigendecomposition method of a square matrix X into U, sigma, and V star matrices. And here U and V matrices are unitary matrices, and sigma is a diagonal matrix. So if we use this original format of these three matrices, it is called the full SVD. And even if we neglect the third term of the sigma matrix, we can still get the same results of X. And in this case, we call this SVD as the economy SVD. And one characteristic of this sigma matrix is that the sigma values are ordered in accordance with their significance. So we can just take several elements of this sigma values to restore this X matrix. And in this case, the U and V also should be in the reduced form, which are called U tilde and V tilde matrices. So the SVD using these three matrices are called the truncated SVD. And the dynamic mode decomposition can be derived from this truncated SVD, but there's a significant difference between these two, the DMD and the SVD, and it is that for the dynamic mode decomposition, we are mostly interested in representing the linear relationship between the present and the future measurement matrices. So for this linearized system, which is X prime equal AX, the Eckhart-de-Young theorem says that the best rank R approximation of this X matrix is equal to the rank R truncated SVD of X. And this theorem can be represented like this equation. So if we substitute this equation into this system equation, we can get this binary equation. And this equation means that this X prime, which is the future measurement matrix, can be expressed without directly using the matrix A. And we can divide this decomposed part into three parts. And the first part is the lambda matrix, which contains the empirical rich values. And these values indicate the oscillation frequencies and the oscillation damping information. And the former part of lambda is called the pi matrix, and this latter part is called the gamma matrix. And pi and gamma matrices represent the spatial and temporal distribution of the oscillatory energy, respectively. So you can check the overall process of the DMD computation from these graphics. And based on the characteristics of this DMD, there was a previous research to analyze the power system oscillation. So in this left figure, this previous work used the empirical rich value to find out the dominant mode and according dominant frequency of the oscillation. And in this right figure, this paper used the pi metrics of the DMD to analyze the electrical coherency between the generators. And in this below figure, it simultaneously used the pi metrics and gamma metrics to analyze the dominant mode and how this dominant mode is distributed among the measuring buses. But we found out that there was no previous research to use this DMD, especially for the oscillation source location. And we think that there's a definite reason why we couldn't use this DMD for the source location problem. So it is that DMD cannot be ensured to give an effective and accurate results for the abnormal oscillation cases. And we divided this abnormal oscillation cases like into four categories like below. And this below figure is the result, which is included in the category 2, where the maximum oscillation magnitude was observed at the known source space. So if we analyze this case with the pure dynamic mode decomposition, we can see that the same kinds of participation factor of a known source space, which is space 6533, has the largest contribution factor, which is much larger than the contribution factor of the source bus, which was 2634. So in order to overcome these limitations of the original DMD, we first proposed an improved DMD. And also, we thought that we can increase the source location accuracy by only focusing on the early stage of the oscillation. So this is because significant changes occur in the oscillatory energy over the time due to various reasons. And so we developed some kinds of two-tier structure oscillation location framework in order to identify and analyze the oscillatory energy only at the early stage of the oscillation. And also because we wanted to use this oscillation detection and source location framework online as much as possible, we've tried to improve the computation and efficiency of the overall process. So I'll go into details of each part. And we can start from the improved DMD. And this improved DMD was motivated by DMDC, which is the abbreviation of DMD with control. And this DMDC inserts current control signals as an additional input of the system equation to divide the impact from the control signals from the system dynamics. So in this improved DMD, we replace these current control signals by the initial state of the measurement matrix. So the resulting system equation will be like this. So the only difference is that we included this Bx init part into the system equation. And if you analyze this equation in the discrete format, we can find out this binary equation where the F means the oscillation dynamics. So this equation indicates that the state matrix A can only focus on representing the relationship between the change of the system dynamics and the change of the oscillation dynamics. And simultaneously, it means that the basic dynamics driven by the initial state of the system will be handled by this matrix B. So you can also check the computational process of the improved DMD from this figure. And as I mentioned earlier, this B part is only the difference in the system equation. But thanks to the characteristics of the SVD, the change of this system equation is only reflected in this U part. And also, fortunately, we can express this X prime without using this U2 part by only using this U1 part. So basically, this X prime can be decomposed based only on this A bar matrix. And you can also see that this decomposed part has a similar structure with the original DMD, which are composed of pi part, lambda part, and gamma part. So based on this improved DMD, we continuously monitor the measurements, whether the oscillation occurs or there is the oscillation in the measurements. And it is called the oscillation detection stage. And if there is oscillation in the measurement, we move on to the oscillation source location stage. So the process of this oscillations detection stage are like follow. We first achieve the online measurements, then we compute the improved DMD on these online measurements. And we only analyze the lambda and gamma metrics of the improved DMD. So we check whether the norm of the energy for some specific frequency is higher than some our specified standard. Then if it becomes over than this standard, we move on to the source location stage. So I think I can explain this detection stage in more detail. And one important thing in this oscillation detection stage is to determine the size of the screening window. So it is because we want the size of this window to be as short as possible for faster computation of the improved DMD and also for the faster detection. But there is some kinds of limitations or minimum requirements for the stable DMD computation because it uses the SVD. So we set the size of the screening window as the minimum condition for the stable DMD computation. And based on this improved DMD computation, as I mentioned before, we can get this lambda and gamma matrices. And from this lambda matrix, we can get which frequencies are included in the current measurements. And by connecting this lambda matrix and gamma matrix, we can see which frequency is mostly dominant in the current measurement. So if one specific frequency other than the base frequency has an energy larger than 1/3 of the base frequency energy, we conclude that there exists the oscillation in the current measurement. So then we move on to the oscillation source location stage. And for the source location stage, we extended the size of the screening window for more detailed analysis of the oscillation. And we set TC as the start time of the screening window and TF as the final time of the screening window. And we selected this TC differently according to whether the disturbance exists in the measurement. And we selected TF so that the size of this source location screening window can be about third time of the detection screening window. So we analyzed this extended measurements in the source location stage, and we redivided the source location stage into two substages. So in the first stage, we are mostly aimed to find out the dominant frequency of the extended measurements and find out only the potential oscillation sources. Then in the second stage, among these potential oscillation sources, we pick one or two oscillation source, which might be the real oscillation source of the measurement of the oscillation. So during the first stage of the oscillation, we computed the improved DMD for the full time. And here the full time means the timelines from TC to TF. And so we can, based on this lambda metric, we can find out the dominant frequency. And based on the pi metrics, we can analyze which bits mostly contribute the overall oscillation energy. And so we propose some kinds of indicator to find out the potential oscillation sources named as oscillation contribution vector for full time in short OCF-FT. And you can also see that this OCF-T can be calculated based only on the pi metrics of the improved DMD. Then in the second stage of the oscillation source location, the first thing we do is to find out this peak times. And there are two peak times, which are high peak and low peak times. And these two peak times can be determined based on the first swing of the temporal oscillation energy distribution, like this. After we select those two peak times, we calculate the high peak time DMD and low peak time DMD, which is the improved DMD computed based on the measurements from THP to TF and from TLP to TF. So if we subtract those two peak time DMD results from the full time DMD results, we can get some oscillatory energy of the buses, which is focused only on this early part of the oscillation. So similar to the OCF after values, we can calculate the OCF for high peak and low peak times. which is time ranges from TC to THP and from TC to TLP. So then we normalize these two factors into NOCF values and the final oscillation contribution factor to find out the real oscillation source is called OCF-TT, and it is the multiplication of these two normalized vectors. So if some specific bus has the largest OCF-TT value, it means that this bus consistently contribute the oscillation, especially in the other part of the oscillation, regardless of whether the total oscillatory energy decreases or increases. So we applied our proposed method into this data set, which includes two simulation cases on double CC systems and one real oscillation case provided by the ISO New England. And I think lots of you are already familiar with this data set because we can download this data set from Dr. Sen's homepage. And from the below table, you can see the results of the proposed method. So in most of the cases, the proposed method can locate the occurring source as well as the oscillation accurate oscillation frequencies within a very short elapsed time, about less than 1 second. And the only case which the proposed method failed was included in category 4. And in this category 4, the measurement at the source bus was not provided. But I think we can, this proposed method can still give some valuable information to the system operators even for this category 4. Then I will go into the detailed explanation of each case. So this is the results on the for the normal oscillation case. So you can check the overall process of the oscillation source location in our framework. So based on the improved DMD, we first check whether which frequency is the dominant frequency of this oscillation. And then simultaneously, we can get the temporal energy distribution and the spatial energy distribution like these two figures. And in the first stage of the oscillation source location, we first find out the potential oscillation sources which show a high OCF active values. Then we select the high peak and low peak times, and then calculate the high peak time DMD and low peak time DMD. And this figure B shows that these two peak time DMDs can give still consistent results with the full time DMDs. And by calculating the normalized values and by multiplying them, we can get the OCF-TT value. And we can conclude that bus 79 is the source of this oscillation, which was correct. But one thing we should notice in here is that in the normal oscillation case, there's no need to analyze this early stage energy because we can still get an accurate source bus, which is bus 79, even when we use the full-time measurements. But this is not real for this abnormal oscillation cases. So if you see this figure, you can see that even if we use this improved DMD results, the source bus 6333 does not have the largest OCF active value compared to the other buses. But if we analyze only the early stage of the oscillatory energy, we can see that bus 6333 has the largest contribution factor values compared to the other buses. And from this figure, you can also compare the results from the original DMD and the improved DMD. So when we use this original DMD, we can see that the source bus has an extremely low OCF active value. So it cannot exceed the minimum standard. I mean, the screening standard, which is in the first stage of the oscillation to find out the oscillation candidates. And you can see that also in this right case, there's a similar result with the left case. So the source bus 2634 did not have the sufficiently large OCF active value, but by analyzing the OCF-TT, we can get the accurate oscillation source result. And the left case is the oscillation case caused by injecting the rectangular forcing signal. And in this rectangular forcing signal injection cases, we can find out some integer multiples of some specific frequencies are also observed. But especially for in these cases, this specific frequency should be determined as a dominant frequency for accurate source location result. So even if some integer multiple of this specific frequency has a higher gamma value than this dominant frequency, we should select this frequency as a dominant frequency. And this right figure is the category which our proposed method failed, but I think it gave a very interesting results. So the largest OCFTT value was recorded by this BES 1002, but there was no any power system components which can arise the power system oscillation. So we need to more discuss about the OCFTT values of the other buses. And when we observe the OCFTT value of the other buses, we think that we could set some kinds of anticipated oscillation source region like this circle. So from this region, we can conclude that two generator buses, which is bus 1131 and bus 1032, might be the potential oscillation source for this oscillation case. And the actual oscillation source bus was bus 1131. So from this result, I think that although the proposed method cannot accurately find out the source, in this case, because of the lack of the measurements, but we can still inverse some quite accurate candidate of the oscillation source and provide this information to the system operators. Yes, and we also applied our proposed method into the real oscillation case. But in the real measurements, as you can see from this figure, there are a lot of high frequency noises are included. So we first applied the low pass filter with 5 Hz, and then we apply the smoothing function to this breaker data. And you can see that noise over than about 4 or 5 Hz are reduced in the pre-processed data set. And we applied the same proposed framework into this pre-processed data. And from this OCFTT results, we can see that line 2 and line 4 of substation 2 have the largest and the same OCFTT values. And the second largest OCFTT value was recorded by line 3 of substation 2. So from this ISO New England map, we can see that this line 2 and line 4 has the largest OCFTT value, and line 3 has a slightly lower OCFTT value than these two lines. So we can infer that the oscillation might happen in the east region of this substation 2, then it may have propagated from east to the west region. So until now, I have discussed about the low frequency oscillation cases, and our paper only handles about this low frequency oscillation cases, and I newly tested our framework into the subsynchronous oscillation cases. But we could not find some kinds of open source for the subsynchronous oscillation cases. We made two authentic oscillation cases using the PSCAD tool. And we injected subsynchronous forcing signal into bus 33, 38, and 39. And we injected signal at 1 second. And we assumed that only the voltage magnitude and phase angle measurements of the line are available. So you can see the first experimental results on the subsynchronous. Oh no, sorry. So I think there are two problems in the subsynchronous oscillation case compared to the low frequency oscillation case, because we assume that these measurements come from the advanced metering infrastructure. So the measurement has a very high measuring frequency, about 10,000 Hertz. So it is very hard to find out the subsynchronous oscillation frequency, even when we use the FFT. And another problem is that because of the characteristics of the PSCAD tool, the voltage ripples were observed in all time span. And it was another reason which made us hard to find out the subsynchronous oscillation. So we first applied the same preprocessing method, which was discussed in the real oscillation data, to this subsynchronous oscillation case, even if it was the simulation data set. But in this case, we applied the 6 Hz low pass filter and the same smoothing function with the previous case. And we also extended the window size for the source location in the subsynchronous oscillation case. So we use much larger number of data points, but in terms of the number of data points, a significantly larger amount of data points were included. But when compared over time, this SSO case has a shorter time window than the low frequency oscillation. So based on this strategies, these are the experimental results on the subsynchronous oscillation case. And as I mentioned, we injected the full signal at 1 second, and the oscillation was detected at about 1.06 second. And by extending the source location window, we analyzed in these measurements. And the OCF values are represented in this figure. So the line 26, 28, and line 29, 28 show the largest OCF value. So from this map, we can see that these two lines have the largest OCF value. And because line 25, 26, and 26, 27 have lower contribution factor value than these two lines, we can conclude that bus 38 will be the oscillation source for this case. And similarly, for the bus 30 line injection case, we could get the accurate result. And in this case, line 39.9 and line 8 to 9 have the largest OCF value, which have larger values than line 1 to 4 and line 8 to 7. So we can conclude that bus 39 is the oscillation source of this case. Yeah, so this is the conclusion of my presentation. So we provided some two-tier structure to analyze the oscillation source. We also proposed an improved DMD, and we applied all of this proposed method into the low frequency oscillation, subsynchronous oscillation, or both the forced and natural oscillation cases. Yeah, so that's the end of my presentation. If you have any question, please really ask me.